So hello all, welcome. So I am Anirudh Sinha. It's gives me great pleasure to welcome you all to this institute lecture. Uh, Dr. Vinod Mengle is an internationally well-renowned researcher in the field of aeroacoustics, and he is specialized in jet noise reduction. So he's going to talk about these interesting chevron features that you would have seen in all our Boeing Dreamliner aircrafts, and he was the principal architect of these chevrons. He was the chief chevron design architect at Boeing when they developed this chevrons. He's also a subject matter expert in engine noise control. So before he was in Boeing, he was a principal investigator at Rolls-Royce and GE, uh, and he specialized in leading teams that solve the nozzle and turbo machinery flutter problems. So he has been across all the engine companies that developed the largest engines for our aircrafts. Before entering industry in 1989, Dr. Mengle was a professor of aerospace engineering at UCLA, Los Angeles, and he also worked at NASA. He is currently the founder and CEO of Aero Insights LLC, consulting startups and R&D firms on conceptual designs for noise reduction of supersonic aircraft as well as eVTOL systems. He is an alumnus of IIT Kanpur. He got his BTech in 1977. He earned his MS and PhD from Cornell University and supported by the John Macmillan Graduate Fellowship. He holds 20 patents and is a fellow of NASA, Boeing, and the American Institute of Aeronautics and Astronautics. So it gives me great pleasure to welcome Dr. Mengle for this interesting talk.
Thank you so much. I'm very delighted to come to IIT Bombay. I'm an IIT Kanpur graduate and I'm coming here after my first interview in 1972 when you have to decide on which IIT you want to go, right? So after that, this campus has changed obviously tremendously. I see the trees and it's superb. I mean, the campus looks really beautiful now, compared to when I came here in 1972. So great. And first of all, I have to thank Professor Anirudh Sinha. And it was a cold call, frankly, I mean, I didn't know him or anything. He knows me, he says so, but then he arranged. So I really am very grateful for getting me here and having this institute lecture. And after this, tomorrow I have a specialized mathematical lecture in the department also. But this is more experimental. Hopefully, I'll try to see that most people can understand, although you may not be in aeroacoustics, which is a pretty hard subject, and noise reduction per se. So I'll try to make it easier, so to say. And let's see if I'm successful in that. Ask me questions at the end because I have a lot of material to show you, okay? So as he said, the title is Innovative Jet Noise Reduction Technology. And most of the focus, or almost all the focus, is all the things I did rather than telling somebody else's story. And it is a story. I want to tell you a story of how I came up with these designs, why do they work, and most of us see it on the aircraft, as he said. Almost all Boeing planes have it now, all the new planes. And 747-8, which is the new jumbo, 737 MAX has it. The older one, what I call older one, 787, is not my design, and I'll tell you why. Because that was before I joined Boeing, and they had frozen the design already, and it wasn't the right one. But I'll tell you, it works for some other reasons. But so it is a story that I'll try to tell you, and more flow physics, more flow insights, no math, no equations. I mean, at least at the institute lecture level, so that let's go on. And one of the main things is this is one of the things. You see the chevrons now on planes, right? If you see, but my contribution was that they're varying, as you can see immediately. And why they're varying? And you must be wondering, what's going on? And then there are also other chevrons here. So my contribution is really, and it really made a slight, let's say, mini breakthrough. So that's the story I would like to tell you. All right. So as an IIT graduate, I also want to tell you my career trajectory, how interesting it can be for those who graduate from IIT. And aeronautics is my passion from 7th grade, okay, and I never left it. I never left it up until now. So it's been 55, 60 years. You find very few, otherwise people do MBA, they do computer science, they do this. No, I was I really loved aeronautical sciences. And now I could go to most of the, I did after 1977, my IIT Kanpur, I went to Cornell, did master's PhD there, and then I joined NASA for 1 year. You can see, right? This. Oh, there is a screen there. And I got invited for UCLA faculty membership, professor. And in between, I went on a NASA fellowship in the summers. It's all great stuff, NASA guys do fantastic stuff in aero, and I was there. Then the industry suckered me in, and there were lots of challenging problems. And I was doing academic type work. So I joined GE in Cincinnati, and then Rolls-Royce was in the Indianapolis area. And I started my jet noise work from here onwards, really. It was a different, I was doing, I'll tell you, unsteady aerodynamics in the beginning, and then I did Rolls-Royce. My main stay was really Boeing, 13 years of Boeing, where I invented lots of things, did lots of lab experiments. They had a fantastic facility, aeroacoustics labs, etc. And when I went for a conference once, I just saw that. I said, I have to go join Boeing in Seattle, and Seattle is a great place, This Rolls-Royce was in Indianapolis. It's a flat place, and somebody's from Purdue, I know. I used to go to Purdue for projects also. But so that was a trajectory. So this was my mainstay. Then I came back to California and joined Parker Aerospace, doing something else altogether. And I didn't like it. So I mean, it was about high temperature sensors and controls for Rolls-Royce engines, again, fortunately. But it was at controls, sensors and controls. So I said, no, I want to do aeroacoustics and not. So I started my own consulting company and doing this research and design and helping startups. As he said, Boom Supersonic was one of the larger ones that I worked for several 2.5, 3 years. And you may have heard about Boom Supersonic. And it's a great company. I've talked to those, the CEO, founder, have had meetings, and almost always it was a remote meeting for me. But very pleasurable working with younger folks. That's one thing I found. As I grew older, there were younger folks coming in, and they have a lot of energy and strength. And I took their help, but led them, and I got 6 patents in 2.5 years. So those were all the new ideas that you churn in your head, and you want to put it into practice. So, but they have taken a separate path now. But that was one, and then, as he said, Aurora Flight Sciences is another company in Boston. I did eVTOL noise with ducted. So that was really the beginnings of that, how to reduce noise even with eVTOL. So this is a different thing. It's not jet noise. It is propellers, rotors, and things like that. So I've covered a whole arena, and I've been fortunate to work with some of the best companies and universities and NASA and stuff like that. So any of you who start off with a aero, you have a great, you can do this thing. That's all I wanted to say essentially. And you have to have luck also, frankly, okay, when you get it at the right moment, right time, etc. But and I have to say, when I started in Kanpur, we had some 8 guys in aero. Now there are 60 plus. I went last year. I gave a similar lecture, so I felt very good. The aero is picking up in India, especially. We get jobs and we get everything else, etc. So with that, let me say, subject-wise, as I said, in academia and NASA, I did theoretical unsteady aerodynamics, the talk which I'll give, tomorrow in the department. But I'm going to talk about, I've moved over to experimental and some partly theoretical. Aeroacoustic jet noise especially is not easy. And I tried it in the beginning. You don't get the right answers. If you give me a plus minus 5 dBs, no good, because that's within the bar, not your margin of error. You want to reduce it by 3 dBs, and you're lucky if you do that. So I said, I'm going to do experiments. And Boeing has fantastic facilities, etc. And GE did also use NASA facilities as well as GE. So I covered lots of labs, etc. Learned a lot during that time. But Boeing, I could use everything and control everything, the labs, So that was fun. For me, it was fun. It wasn't work. I have to say, it wasn't work. Never. This was all fun, fun part. So basically, but I moved from theoretical to experimental, 75% experimental, 25%, etc. And so let me give the contents. What I'll talk about today: introduction, jet noise 101, generation and reduction. Because before reduction, you need to know how is it generated. Otherwise, how do you talk about reduction? So at least some basics, and I'll give only engineering basics. There's no point in giving into the whole details. It's a pretty difficult subject, and in 1 hour I can't compress everything. And the main focus will be 3 and 4. New noise reduction concepts I introduce. I don't want to tell about other work, etc. because it has gone into product. That's one of the most successful things that has happened for me. And you can see it. So it's a nice thing, and you should know why it works and things like that. And my focus is from first principles. You go to the first principles, apply flow physics, and apply simple ideas, and then check it out, whether it works or not. through lab and experiment. So you have to do scale model test validation every time. You may have great ideas, but they have to be tested. People have, lots of ideas and they don't necessarily work. They don't necessarily work, or they work with some losses. And as you know, if you're an aero, you don't want thrust losses, right? You can reduce noise as much as, and I fought for it in all conferences, right? You have seen me in AIAA meetings, aeroacoustics meetings. People have lots of ideas, but then they have thrust loss and you don't need that. So how do you do it? That's the engineering challenge. You want less noise and you don't want thrust loss. And you want to at least keep it same or maybe plus minus something, right? So I'll focus on this. If I get time, future concepts, and then summary and Q&A. Okay, so let me see how it goes depending on the time. So I need to do some basics because not all of you are familiar with, you may not be noise people, you may be aerodynamics people or something else totally. So I just want to do some very basics and I'll cover pretty fast. First is sound pressure level. Some of you may know it's a dB thing, a logarithmic thing, PRMS or Pref squared and 10 log. So it's a logarithmic thing when you say, anybody says dB, oh, I get 60 dBs of noise or whatever, right? And the reference is the lowest threshold of hearing is 20 micropascal. One key thing I would like to tell you is that when you add x dB plus x dB, it's not 2x dBs, it's a logarithmic addition. We are adding P1 RMS squared, P2 RMS squared, and then converting it. So what happens is, it's just x plus 3 dBs. You may have 50 dBs plus 50 dBs, the answer is 53 dBs. You may have 100 dBs and 100 dBs, the answer is still 103 dBs. It's not 200 or anything, you just need, you need to get it into your head. Another thing, because of this logarithmic definition, is x dB plus y dB. If the y dB is really, really small as compared to x, like lower than 10, the answer still remains x dBs. So, and you will see the repercussion of this. If there are two sources and you keep on reducing y, it doesn't matter, it's going to be x. You will see that, very, very shortly. So that's SPL, it's a frequency dependent, PRMS can be frequency. So it's a SPL is a frequency dependent phenomena. And also directivity is there, which direction, what distance. So we talk about far field and I'll come to that later. The other unit I'll use is overall SPL. What does it mean? This was frequency dependent, now you integrate it across all frequencies. So you draw this thing, integrate and you get one number, which is called overall sound. So to just give an idea about the OSPL, these are the kind of dBs we talk, and threshold of hearing is 0, but if PRMS is equal to P is log 1 and it's 0. So that's the beginning. It's a threshold of hearing. We can't hear, humans can't hear below that. Then typical quiet bedroom is 40, noisy bedroom, I don't know. It could be long, right? It could be higher. Normal conversation is 60 dBs. So that's the kind of thing in your head, but it's OSPL. A truck about 15 meters from the distance is about 80 dBs. And then we have music concert, not that loud, still is 100 dBs, OSPL. Now here comes jet plane, 30 meters. And you see that I have to give a distance also because noise decreases as 1 over R square, right, in the far field. So in some of these which are bigger, 130 dBs, overall SPL is pretty loud, okay. Remember this threshold of pain is 140. Then you start saying it's paining. But this is a general scale and we'll be somewhere here, in this, and we are trying to reduce it. And it's not the OSPL, and the reason is because our human ear has different perception of different frequencies. So what happens is if it is 3000, 4000 hertz, it feels more annoying and they have definite formula, etc. So we try to focus on those which are annoying frequencies. You may reduce a lot about, or at least not increase, let me say, the 3000, 4000 hertz because it will feel annoying and people say, although SPL is same, no, this is louder or it's just more annoying. So in aircraft, which is a community thing, right, and people say, no, it's annoying. The perceived noise scale is another thing that I'll use. It's called PNL and PNDBs is a weighted frequency scale. But you can see that still it is not, it's like a spectrum, right? It's a function of the frequency, as I said. And for certifying planes, you just need like one metric, what do you do? A plane just flies across, over your head. So the whole time history is there of the pressure, right? And so they use effective perceived noise level. And that's used for certification, the planes cannot pass otherwise. They had to follow certain rules and I'll show you where they fall. And that's called, it's an integration of the PNL over the different frequencies, time, etc. And it includes some other effects also like peak PNL, time, and these are the details. But you get one metric. It could be below the plane. It could be on the side, and there are distances, etc. For certification. And it is also when the plane has taken off and a certain height, 35 meters, etc. And so there are 3 points that they measure, EPNL, and you have to be within all those limits, and only then the plane can take off, guys. It is a very strict certification rule, because otherwise community noise is a problem for the people who live near the neighborhood of airports, right? So this is just the basics. So what we talked about is SPL, dB is everything, OSPL, integration, PNL and EPNL, and these are all measured in dBs, but they are different scales. So when you hear somebody saying so many dBs, you see which dB is this? Is it EPNL, PNL, etc. So this was just 101. So why reduce aircraft community noise? Why reduce? As you know, I mean, and you are in Mumbai of all the places, and the noise is so much in the roads. I'm talking about aircraft. The airport, the traffic has increased considerably, and it will increase, keep on increasing. And the airplane size has increased. You remember, has anybody sat in an Airbus A380? I came just to fly with that. It's so huge. You look at some other Boeing 737, it looks like a small thing. So bigger the plane is going to make bigger engines, bigger noise, etc., right? So community noise is increasing, and the complaints, especially in Europe and US, I don't know how it goes in India, frankly, because I'm not used to it. I think people just don't complain or something, but this is a very important issue. I live in a town called Arvine, where is strictest airport control. People will go and just write to the senator, whatever. And so you have to be within limits. So it is very strict in US, in some of the airports. London Heathrow is one of the key examples, They also have a quota system and all that. But anyway, so noise may impose fundamental limitation on future air transportation growth. That's the key thing. And we want to reduce that slowly, because there's just more people, they want to fly. So how do you do it, right? So quieter air traffic, if it is quieter, it can go deeper into nighttime and early mornings. So obviously more flights, and the airlines get their bottom line more and stuff like that. So there are advantages. So jet aircraft noise became a critical goal of NASA's even 3 pillars, which is very not unusual, but being the topmost in the first 3 priority, and this was 1995, okay? And they wanted to reduce perceived noise 4 times in 25 years. This was 1995, now we're in 2025, so it's 30 years. And let's see if you are successful. We are. So I have to just jump ahead and say, we did it. And small things like what I contributed, they are small things, but they contributed towards that. And I'll show you, that's the story I want to tell you. So this is the status of, this is the limit that FAA or Federal Aviation Authority puts, okay? You cannot, stage 3 was like a reference during the 1980s, 2000. All these planes you see, they better follow, they better be below that limit. You can see A's are all Airbus, B's are Boeings, MD's are McDonnell Douglas, and it was a separate company. And now stage 4, and I'm just going 2020, here is our 2025. So that's the stage 5, they're coming up, and there's certain different stricter rules. So here you see A380s makes pretty low noise, okay? I mean, they're well below, and they don't have chevrons, and we'll learn why and why not, etc. But Boeing planes, the newer ones, especially here, this is not even captured. This was, and by the way, I'll show you all this open literature, open data. There's nothing that I'll show, so you can go and look at all these references that I've given. If somebody wants to look deeper, all those things, my papers, everything is given there, and it's all open literature. I can't tell if it was IP or something. I just can't tell. You may ask questions. I'll say no. I can't answer some of the details. But that's the way it is. Now I want to show you. This is commercial. This is F-35 is. They don't care about noise. This is a vertical, hopping F-35. It's so loud compared to that era when it came up, and it's stage 4. Commercial guys have to do this. Military guys don't care. Same thing with all these all the jets that you hear, F-18, 16, they're way above, and they don't care. Recently, they started caring because they were taking off from Navy boats, and the community started complaining, you cannot make those noise, you may be military planes. So they came back to us, in Boeing days. Navy also, meaning they wanted to reduce shock cell noise. I'll get to it later. But Concorde, look at Concorde, he's a commercial guy. During that time, he's way up whatever the stage 2 was meant. So they used to pay enormous penalty when they landed, when they took off. And that's why the market, one of the reasons for the failure was they paid a lot of penalty when they took off and landed. This is enormous. And marketability, you can't, you can make the seats higher, but it doesn't work and it failed after some time, right? So now what I worked with some of the, like I told you, I worked with Boom. They will be here, okay? And they will be supersonic and they will fly over land. They just proved it 2-3 months ago, and I saw the whole live video. It's nice, the idea is nice, but that's for a different day that I can say. So let's get back to motivation still for jet noise reduction. And this is like a basic, if you have not heard about, propulsion and turbo machinery. So this is the basic sketch of a turbo fan engine, which is the modern engine. Huh? So we have a hot flow. First of all, we get a compressed flow here. It is a compressor. It goes through a combustor, which makes it hotter and gets, you can extract more energy out, and you throw out hot core jet essentially. That's hot. The inside one is always extremely hot. The outside one is not, it doesn't go through a combustor. We call it fan flow, and it's cooler relatively with respect to the hot fan here. So here you can see there are already two streams, hot and fan. And things are going on with their mixing here because there's a shear layer. Now it'll get slowly into fluid mechanics, right? Also, this guy mixes with the ambient because the plane is going forward. So there's a shear layer which develops. So that also will make noise. So the whole key point will become as to how to reduce this noise coming from the shear layers. And I'll show these are the sources. So if you look at engine noise of this sort at takeoff, there are several components, the fan inlet in this direction, the fan exit is pretty large. Combustion, turbine, airframe during takeoff are pretty low. This is typical of a modern plane. Jet is also, pretty large. So fan outlet, on this side and jet, and I'll show you the angles too. They are the topmost. Now you remember X plus X dB. So we need to reduce this guy. If I reduce this guy doesn't matter. It won't change. X plus Y dB, remember what I showed? That if you reduce the Y, which is much smaller, doesn't make any difference to the total. So the whole goal has to be reduce these biggest guys first. Okay, and I have worked on fan, but today's talk is on jet. How can I? They're fairly comparable during takeoff. During approach, different. Jet noise is not that important. The airframe, right? Fan is still important, and the airframe rises. But my focus is really on takeoff noise, which is the worst case scenario, so to say. And there is also directivity pattern. So as I said, jet noise typically is largest at this angle, roughly 130, 140, etc. It is exiting, right? Fan out, which I showed there, is somewhere here. Fan in is, so there is a peak directivity also. So we talk about frequency, we talk about directivity, and distance is far field, so it's 1 over r square is what we assume, right? So this is what I just said, and my focus would be on jet noise reduction essentially. Now there are two types of nozzles, and I'll talk about both because I contributed to both of them. And although my focus will be chevrons, there is a whole bunch of other types of jet noise reduction devices which I did a lot of innovative things. So this I just explained, right? This is, so, and I'll show you what chevrons are, but these are like little serrations that I showed in the beginning. You can have it here on the fan nacelle. We call this nacelle somehow in the industry instead of nozzle, and the hot one is called nozzle. So we can have also chevrons here. However, here remember this fan flow is open to the outside immediately. These are big guys, okay? These are for bigger engines. Whereas in smaller engines, if I contain that fan flow, there is a possibility of mixing it by some means inside the nozzle, right? And there is a thermodynamic efficiency increase if I mix it inside. If it is uniform here, you get fantastic, the thrust efficiency is increased. So for smaller engines is possible because you do not get that much weight and drag for a smaller diameter engine. Whereas big guy, this is big, I'm talking about this is G90 is like 10 feet, 20, I'm 6 feet, okay, and plus. So this is 10 feet, 12 feet, the whole diameter. So their weight, drag will increase and you cannot have a long guy. You just have to come up with some innovative means to reduce it. So both of them, we call these long called internally mixed nozzles because it's mixing, and I'll show you a lobe mixer. This differs from a chevron, what it does. So I just said, large engines, commercial, subsonic, and all the boltings, I worked on all of them. Rolls-Royce Trent, not really, but G90, NX, CFM LEAP, these are the engines that go in the planes that you see these days. Whereas this is on small to medium engines. I've given the thrust range here. Commercial, subsonic and supersonic planes, I was saying, I worked on both subsonic and supersonic. Rolls-Royce days I worked on subsonic. And later on I worked on supersonic. In GE days also I worked on supersonic actually, and then recently. So A380, the Rolls-Royce was a smaller engine that I worked on. So one of the things I was talking about thrust and noise. So you'll see it immediately. It's only the one formula that I'll show, and it's not really formula. So noise, very roughly speaking, I don't know what the sign is. I didn't capture the sign. So it's just approximately proportional to, okay. I think PowerPoint changes when it goes on the monitor, I'm sorry. But what it says is the jet noise with so-called light hills theory goes as 8 power of jet, very roughly. We are talking about engineering thing. However, thrust, if you see, goes at V jet square, right? Momentum is the momentum, and there is an area term. So if I reduce this just to reduce jet noise, my thrust is also going to go down, but at a lower pace, V square, right? So what we can do is, if I want to reduce V jet to keep same thrust, you increase A jet. That's what Airbus does. Just increase the damn size of the engine, okay? So bigger it, but you have other losses. You have weight, thrust. So it's not a intelligent solution. Let me say that way, because you're increasing weight and drag. And that's not smart engineering. So this is simple for that, right? And you need to compare it for same thrust. So what they do is, if you increase the bypass ratio, what does it mean? Bypass means the mass flow rate coming from fan and its ratio with the core. It's called bypass flow rate. This is called bypass flow. So typically, 5.6 to 9 plus these days, if you increase the bypass, then no jet noise decreases because of the reason that velocity decreases. But you cannot keep on doing it, you cannot keep on increasing the size of the engines. That's just not right, guys. So there we have to come up with newer methods, and those are the kind of methods that we came up with. To tell you the bypass ratio, Boeing, NASA has tested up to 20, making this core smaller and smaller. That's another way, right? But you cannot make, because it's the most energetic portion of this whole thing which gives the thrust. So they have tested in Pratt Whitney and GE days, they have tested 12, but it hasn't gone, I don't believe it has gone to production. So the other thing is, this is all right, I believe in reducing at the source itself. So first you need to know the source, and if you reduce the noise at the source, then it is a good solution. And we'll show where the sources are, etc. So chevrons came up in around 1995, and GE had the first patent on that. I must say that my colleagues had it. I didn't work on it, but then I worked on something which it beat GE chevron. We always used to ask them in Boeing, give us your best shot on their engine, and it was nowhere comparable. So they said, yeah, we'll accept you, because they can sell more engines, right? If it makes less noise without thrust loss. So in 1995 the whole thing began. Okay, this business about serrations and all. So here, for example, medium bypass ratio of high-ish and lower, typically exit. I mentioned this. If it is uniform, then the thrust, it came really for thrust efficiency increase, not for noise. These lobe mixes, and I'll show you a picture. What I'm showing you as triangles. It came because thrust efficiency. The outcome also, side effect was that it also helped noise reduction, and external jet noise is. See, I purposely wrote external jet noise. What I mean by that is the noise made by the flow or the jet outside this whole nozzle. But there's a whole bunch of mixing going on inside, right? Do you think that will make noise? Right? And it will make a lot of noise because it is small scale and it is high frequency. What did I say about high frequency? Perceived noise is annoying. And I have been trying to convince, I can't believe these are old, these are earlier designs, as I said here. So I had to convince NASA and everybody that internal jet noise, I formed that term. Internal jet noise is important, guys. It also will go out. It's not going to contain. It will go out like this and it will refract. And you will see that as a high frequency noise. And people didn't pay too much attention when I tried to bring it in meetings and stuff with GE and NASA guys especially. And during the, what we call the second generation Concorde days, that was when I was in GE. So it was like early 90s. But now I'll show you, I wrote lots of papers and things where it is important. It just is important. But there are also ways of reducing it. And I came up with some other solutions for that. So reduction at source, again, I'm interested in reducing at source, lobe mixers. They have started in 70s, but they never improved after that point. And I made some improvements. So in that area also. So now let's see the scope of this lecture. And I'll quickly go through this. I'll try to tell you the new concept and design. As I said, it will be first principles, flow physics. We tested it in model scale. What I mean by isolated nozzle, remember this, there is this some sticking out, a pylon we call it, because that's the one which goes underneath the wing, all right, because you have to attach the engine something, and that pylon creates some difficulties because it's no longer axisymmetric. Like NASA always does very nice things, academia does all the nice axisymmetric. No, it's not, it's non-axis because of pylon. I'll show you how it does. And then we also tested, we have a nice scale model here in used to have in Boeing days with a half wing model, and it kept in a wind tunnel which simulates the forward motion, right? So there are 3 streams. Very few facilities have that, even in US. The hot, the cold, meaning hot core, cold, and then it's kept in a stream. They will have only 2 streams or some, because it's just expensive. This whole business is very, you may have, I know you have worked there in the OSU and stuff. And it's very hard to have these whole 3 stream things with the big wind tunnel and all. So, so after testing it, if success is there, we go full scale. This is full scale, and I worked on it. So this is the same thing, as you can see. And we call it Quiet Technology Demonstrator Program, and there are lots of people who contributed to it. But when it goes to full scale flight test, it's a wholly different beast, guys. It's very expensive, number one. But people like Boeing, at that time at least, they had deep pockets. Maybe not now, but but they had. It was, for me, it was the best time to be at the right time, right place. Golden era, we called it, of second golden era of aeroacoustics. So I took part in this and all, and then it goes into products. Now this is the 747-. Then it goes into different teams. It goes into 737 MAX also, etc. So now let's do jet noise generation. I hope I'm not going too slow, but it's okay, right? Well, I need, if they understand, it will be great, So let's look at it very carefully. How is jet noise produced? In a very simplistic terms, I'm not going to go into fancy and classic concepts. There are newer and newer things coming up, So here is your nozzle and just one jet for the time being. It has a speed, it has some velocity profile, VR, radial, there is also temperature profile, right? That means, and this outside one is obviously lower than jet speed. So it's going to create a shear layer. That shear causes turbulent fluctuations in the orthogonal direction, and that's the source of noise, really, very simplistically. So I'm just showing here, represented by turbulent eddy, the red guy, which is moving forward, convecting, right, at some speed, etc. The fact that it is convecting in a moving flow, if you try to look at its ray that goes out, it will refract inside the jet even, and then it goes out straight, and that's how the observers see it. So there are several elements to this simple model, and I have worked on the mathematics of this also, and I will not go into it. But these are the kind of modules, and this is a very classic. Marv Goldstein is like one of the guys who have written the Bible of aeroacoustics. I worked with him in NASA. I was lucky enough to work in that group, etc. So and G, I have to mention G. There's a Ramani Mani, famous guy, okay, in aeroacoustics. These are all gold medal. They got gold medals in the AI meetings and all. And I worked with him. He was my colleague really in GE days. And he was a Caltech guy, extremely bright guy, okay. And Ramnaran Duria College, if you know, he was from there, from my college. There was no IIT those days, but he very bright guy. Ramani Mani is the name. So I learned a lot from these guys, okay. I mean, they are amazing people. The concept, the way they understand the subject is really amazing. So turbulent jet, they are convecting turbulent eddies. There is a source intensity spectrum. Each source is not one frequency that is going at. There is a continuous spectrum, and they move. So what moving sources do you know? It has a Doppler shift. The frequencies change for the guy who's stationary with respect to the nozzle, but this is moving. So, but what you may not know is that there is something called convective amplification. When a source moves, the guys who are in front of it, also the amplitude increases, not just that the frequency increases. And those who are behind, the amplitude decreases accordingly. And something that may not be well known, to people is, it's called convective amplification. There is yet one more complicated thing that happens. It is called flow acoustic interaction. So one is refraction, which is understandable. There is now something else to it called fluid shielding, and I'll explain briefly in words. It is all mathematical models are there for this. Because of these gradients, what happens is sometimes, depending on the velocity profile, temperature profile, the jet, this ray that I'm drawing, even for high frequencies, it can attenuate inside the jet, and what little remains will still go out. That attenuation is called fluid shielding. and there is a certain function which is a combination of velocity and temperature profile. Very interesting effect. Professor Balsa, he was in GE those days, famous guy, JFM, Journal of Fluid Mechanics papers, and he worked with Ramani Mani, and I got to see them after many, many years, of course, but excellent work in fluid shielding. So that's the classic theory. Okay, these days there are other ways of looking at the same phenomena, etc., and then it goes into the far field. So the idea is, if you want to reduce the jet noise, you have to reduce it at the source itself, source intensity, and the source, the shear strength. It is depend on the shear strength between adjacent flows. So how do you reduce shear? The key word is enhanced mixing. If you are mixing this, the jet is spreading, and if you enhance it, whatever means, then there's a good chance that the jet velocity will decrease much faster. That's the kind of the heart of the problem. And how does the chevrons reduce it, etc. I'll show you how it does that. So let's get back to the earliest, the Gen 0 chevrons which GE developed. So this is NASA and GE work, and I was part of it. So, but the other folks developed all these things. They are just cookie cutter triangular in the first. Okay, this is a very zero generation, I call it. Nothing fancy about it really, but they want to just try out and see how it works. This is the baseline. As you see, all the older nozzles, they have nothing. They're just round, smooth nozzles. The edge is smooth, and the two jets come out, etc. So they want to try out. These are the chevrons, the serrations that I'm talking. What happens is, this chevron I'm looking for front looking, aft looking forward, or either way, they create a pressure underneath and they create vortices, right? Just like wingtip vortices you must have heard. They will create vortices. I give always an analogy is that if you take a teaspoon in a cup and then you do like this, right? These eddies come out. That's all it is really, okay? Turbulent eddies, and we call it, the difference is, so you can see that the flow will come out here. So if this was cold, the hot red will come out and the fan flow will go down, it will generate, right? However, the direction with right hand rule is in the streamwise. The vorticity direction is this, my thumb direction. So that's the streamwise direction, flow is coming out, right? So when you ingest streamwise vorticity in a shear flow, it's known that the mixing will be enhanced. And I'll show you what I mean by that. It's known through basic scientific experiments, the streamwise vorticity. So we are trying to control that, the vorticity, the streamwise vorticity. And this is the dominant mechanism, the others are subdominant, so I won't tell. So what do I mean by the spreading of the jet is the following. This is just a plate, I'm showing one plate. There are two flows, one larger, one smaller. So if I don't have chevrons, I'm just showing it with the blue, that's the spreading. It will spread because it takes ambient air, right? Ambient air from outside, meaning the red, in this case the blue and the red, and it will just spread slightly if you define it in a certain manner. And if you draw by simple engineering, you get a gradient which will be, let's say it is 0 outside. So it will be from here to there, and it will be very sharp gradient. The gradients, remember I said, creates noise. Actually, there is a formula, as to what power, etc. Let's not go into that. Now, however, let's say, so the gradient is du dr, right, as I said. So if you now decrease, how do you decrease? Let's say by some means, and I am not even saying how I'm going to increase the mixing. If I'm sorry, folks there, that said, can't see the thing, unfortunately, when I'm there and blocking their view, I'm sorry. So somehow if we increase the mixing, what we are saying is the spreading of the jet is bigger, the red guys. So what happens? Why are we saying that? Because now this gradient goes like this, that du dr is smaller. Simple engineering, okay? There are lots of other complicated theories. So simplistically, but we also at the same point are increasing the area, the annulus here, right? If it was a circular nozzle. So increase in area, but the gradient is it. And the power of the gradient is more important, is more powerful than the area increase. So you will benefit if you decrease. But that can happen, downstream. You may be doing something here with the small scales that you introduce perhaps. It could be the high frequency, and I'll show you data. That's where these nozzles failed, frankly. And the kind of thing I'm going to show you, you'll see the data is the king. So the data will show you. But that's the key idea, okay? Reduced strength of jet noise at some frequencies at least. Now, if you had another plate or it was a circular nozzle, you will have this thing spreading, right, from both sides. So these shear layers will meet here instead of meeting here. So if they meet here, and if you trace, how the central line velocity, for example, it will decrease much faster. This is still same, right? So your potential core has decreased due to mixing. That's basics, right? And so if you look at the central line velocity, I was telling you about the 8 power. So this is a simplistic view of looking at things. Without the mixer, it is like blue. With mixer, the potential core, we call this flat thing, and it decreases. So at each slice, if it contributes, this is going to win. That's the basic, enhanced mixing with streamwise vorticity. That's one lesson from this. Now, how you do it, the details, that's what gets more and more interesting. These are the basic right now. We are just beginning things. Huh? So let me see, where am I now? So short cowl. So this is still the GE test that we are doing, but there are different. They said, okay, why do I just immerse it in chevron? I can have up, down. We didn't know exactly what we were doing that time, and it's my colleagues doing it. I wasn't part of it. I was, I analyzed some of the things later on. I was a junior guy that time in GE days, but then I could understand this and do much better than what. So there is alternating chevrons. This AC is alternating inside, and the same just cookie cutters outside. The C is for fan. The first letter is for A is for the inside core. Please remember, you'll see now lots of symbols popping in. The first letter is core. In this case, A means alternating. C is just a core chevron, just a straight line. Huh? And I means they are internally depressed, in this case the core, and C is same in this case. So now you look at what these are uniform chevrons, okay, they're just the same cookie cutter all around. Now we'll look at some data, and I don't want you to get confused, it's getting slowly, too much data I don't want to give you, but still I have to show these things, and these are all published, okay, by the way, I mean I show you, right? I'm an author of that, I think. And we couldn't release this for 10 years. Imagine if you go in US and you say for freedom of data, right? NASA said we don't want to give it to Airbus or Europe. So they kept it for 10 years. We did all these tests long time ago, and then they released it, and I had joined Boeing by that time. So I saw my name, I said, wow, they still want to keep my name after 10 years because I contributed something at least that time, It was really, lots of colleagues did that. So this is BB, which is the baseline. So the black guy baseline, huh? Everything is baseline, pretty noisy here at the low frequency. And then it goes down, all right? Just quickly, the internally dipped chevrons, it reduced the noise considerably, right? Green guy, reduced the noise. Now there is a slightly, it goes up in the high frequency, it pops up. Remember what I said, 3000, 4000 hertz, things start getting, perceived noise level it penalizes for those frequencies. So, and it does, although this you may win here, you may lose just because the small increases, okay, sometimes, not always. Now look at this other guy, AC, it did even a great job at very low frequencies. Red, this you can see how many dBs it is, it's quite a bit. But, look at the high frequency increase it starts giving right here. That's no good. And in some NASA works, I've given the reason for this, why these alternating chevrons. But however, this is only at one of the angles. I showed 90. As I said, noise is a multifaceted. You have to look at all the angles because the plane is going to go and the angles are going to change for an observer. So it's fairly, now slowly it will get complicated because this is just 90 degrees, which is a reference, from the nozzle exit plane, what I've shown. You have to look at all angles, integrate it, and I'll show you how we do it slowly. And hopefully you'll keep up, with that. So it turns out the IC model, the middle guy, gave 2.71 EPNDB. Remember, effective perceived noise, that's one metric. So this is for flyovers, I believe. This is when the thing flyovers, takeoff noise. And the thrust loss, etc., if there is any, we should talk about at cruise. Takeoff is only a minute or so, 2 minutes. But cruise, you don't want thrust loss. So you run it at different operating conditions, right? So the key thing is, there may be some thrust loss during takeoff, and that may be acceptable. But in cruise, you would like to have not much thrust loss, otherwise the airplane will need a lot of fuel, and that's no good because their tickets will go up, the airlines will start charging. So see this, even this, this is a thrust coefficient defined in some manner, measured upon ideal. This is large, this is at least small. So as chief engineers and propulsion engineers, they'll say this is still acceptable because this is within margin of error really. This is all model scale, okay, that we are talking. By the way, they cannot measure thrust when the plane is flying. There's just a way to measure it. They have to keep the jet engines in a thrust stand static. Then they can measure with strain gauges and things. But when a plane is flying, it's all indirect to the wakes, wake profile deficits and stuff like that. They cannot measure the thrust of the plane when it is flying unless we order to react and stop it. You don't do that for a plane, right? But you can do it for a jet engine when it is on a static thrust stand. And we used to do that in GE days. They are big thrust stands, there are strain gauges and everything. So they can measure actually also. And they just take it over for this thing. So EPNL, the problem here, as I mentioned in the beginning, was these EPNLs, this is NASA stuff, not mine. EPNL was found at same nozzle operating conditions. What happens is you keep the same nozzle operating conditions, the fan pressure ratio, temperature, nozzle core, and then they check these noise. But it may produce different thrusts, because if the thrust efficiency is like this guy may produce low thrust. That means you give me concept A, concept B, you're not comparing it as saying, okay, this guy is a great noise reduction, but if it makes less thrust, not right. And I fought for this, frankly. I was one person, they used to draw these curves all the time, and you may be very familiar. And I was one, he knows, he's smiling here. In aeroacoustics conferences, whenever I raise my hand and say, but the thing is, aeroacoustics guys don't measure thrust. It's very difficult in the labs to measure thrust. So you have to go to propulsion lab, and all those things are available for companies like Boeing and GE, but not in academic. So then they say, can't answer that question. Was there a thrust loss or not? And CFD doesn't help. It didn't used to help. Maybe these days it has grown so sophisticated. And actually I did that with the boom guys. They can predict very well. They tested it in labs. So I'll say, yeah, I mean, that's salute to that, after so many years. But noise, no, they can't predict noise with all the fanciest tools that they still have, because it covers a whole bunch of frequency scales, length scales, what we call, right? So anyway, so then what happens is they had to do the resizing to get the same thrust. That means you're changing the area, you're not comparing apples to apples. Not right. So it's always something or the other. You cannot change the size of the nozzle. You're telling me a concept, keep the size the same, come up with some nice idea, keep the nozzle operating conditions also. You cannot change it, because that has been governed from lots of other things. Then you say this is what it is, and give me a concept which will give me similar thrust, if not same exactly, but at least let's compare things. And it takes some effort to convince NASA guys and company guys to even to me now it seems simple, or to you may say, of course we'll do that, right? No, it's most of the people didn't know that in the first place. So when you do something different, you have to fight it out against the whole system. And I'm not in academia. I was in academia, but I have been in industry for 38 years, and I've seen how it goes through NASA, industry, everything, So I've already said, low frequency does decrease, high frequency is the key, and the cruise thrust coefficient does go down, as I've said. If it goes down, not acceptable. So how do we improve? Remember what I said earlier, these are uniform chevrons, meaning each is same. They are azimuthally periodic. Peripheral, that means, right? Circumferential are the same, cookie cutters, right? And no account of asymmetry due to pylon, I told you earlier, or wing, or flaps, and where the observer is down here in community case. In airport maybe side, but basically community noise. Upstairs I don't want to make noise up, throw the noise up maybe. So some people came up with that, do something up and throw the noise, but there are cabin guys sitting also, so you have to reduce that noise too. But that is not as important, frankly. I know as passengers we would like to have quiet, right, cabins, and they do other things for that. But you want to reduce really community noise, which is directed. So direction comes in and frequency, and that's the point. So how do you do it? And first let me show how asymmetry is created. So this is a CFD plots, just simple rants we did long time ago. My colleagues run the CFD. I'm not a CFD person, so it's a teamwork always. And here it is without a pylon. You can see the turbulence intensity I'm plotting, turbulent kinetic energy. And once you put a pylon, you see that there's a whole turbulence intensity up near the pylon. I'll show you why. Remember I told you first principles, flow physics, and then I'll show you why, what we need to do. So you see that, and surprisingly, only Boeing used to run with pylons, all their tests, since ages. All the engine companies, NASA, they never had a pylon. So they always did nice, round nozzles, no pylon. So they couldn't understand the non-axis symmetry in this business. And they never did anything about it. And we started doing it, and I was the lead on that. What does it do? It creates something else going on. So, and this is CFD, and we have done experiments which show this, which capture this, that there is a lot of intensity. Now, first let's understand why it's happening, and if you understand that, then we can see how to reduce it. So that's the idea, right? So here what's happening is, this is the side view, this is the pylon, my cartoon picture. The core flow, even in that CFD, it is clear, it sticks, even it's not coming exactly center line, it goes slightly up. Why? Because this is called Coanda effect. Maybe some of you know, right? If you put a spoon in a tap water faucet, the water will stick to the, it's a concave, right? It sticks, and that's called Coanda effect. Here is due to Coanda effect, it's high speed, but still it goes up, slightly up. So what happens, this is a very high speed core jet, it will meet your ambient flow, which is slow speed, so the shear will be even higher, just because this is right. On the other hand, also, the fan flow, because of the pylon, this is blocking, it's a blockage, and it could be as much as 90 degrees, okay, in reality, because I actually have designed these things. So it is huge blockage, so 1/4 of the circle is gone, is blocked. If it is blocked, the flow has nowhere to go, the fan flow, but sides, and it's also going in the front. So when it goes to the side and that, it goes down, the net effect is like, it goes down near the pylon, not below it, not here, but near the pylon. So what happens is, now you have a radial component up and down, and that creates itself, a lot of turbulence, additional turbulence, which is not controlled. Meaning, remember we said for chevrons we have streamwise vorticity, which is controlled and all. But so this creates, and general there is a pylon wake too. There is a pylon wake coming. All these things nobody took into account, and that increased TK. So what do you think the solution should be? If I'm increasing the TK, I said, remember, source, decrease noise, and this is a source. I want to decrease it. What would you do? All those chevrons, I said, hey, have more vorticity up. That's the azimuthally varying chevron you saw in the first picture. That's as simple as that, okay? So because of the interactions, I said, okay, why not use, now what happened here? Oh, I thought something happened. Highly asymmetric flow. So what happens if I enhance the mixing near the pylon? And at the same time regain the possible thrust loss, because if I did it all across, if this immersing of the chevrons creates some thrust loss, because it's like a drag, okay? Vorticity is not generated without, there's no free lunch. So what happens? So I said, if I don't need it, I'll make it smaller. I don't need to mix it. That's why, and the first thing that comes to your mind, excuse me, is azimuthally varying. And you can have linear, you can have all, but I don't know whether linear is better than this. So first is linear. And you can do that by varying the lengths. And then later on, we also did things like, you can keep the same length, but dip it differently, right? And I'll show you, we did it with even shape memory. That is one of my last things. That was like pretty sophisticated, I thought. And we actually ran it on planes, but I'll get to that later. So, appropriate tailoring of axial vorticity around the periphery of the fan. So it's a tailoring of vorticity. You want to tailor the axial vorticity differently. More near the pylon, less away. And maybe the thrust loss is recouped, meaning we don't even have thrust loss. That's the idea, that hopefully I can reduce noise without much of a thrust loss. So it is, the engineering idea is simple, okay? It's not really big deal or something, but nobody thought of it. I first thought I got a patent, I have several patents, and there are several different nuances to it. So let's see what happens now. This is Gen 1 chevrons uniform. So remember, first letter, the R and R I'm showing, the core and the fan, and then T fan. First R is for the core, which I kept uniform. I just wanted to check the effect. Why do I call it T fan? Because top enhanced mixing. That was my everybody in the industry calls it T fan now. I gave it the name because I wanted top enhanced mixing in this side view. And you can see I've just started with playing with the lens. And there are all kinds of things, and you were asking me, so what's the number of chevrons? How do you decide? How do you decide the angle? I can't tell you anything about it, but we have to experiment with those things. That's the IP things, etc. Okay, with companies. But we came up with this, and it's also trial and error. I have to admit that. Okay, and we understand something. So that was my first patent, and then I published. You're asking a whole series of papers, and when I first presented actual data, it was standing room. It was in MIT, in Cambridge, one of the conferences. Fantastic. It was like. And a whole bunch of papers. I had 6 papers out of 7 in that one session, and it was just about this business, So we did very lots. It's a teamwork. I have to say, it's a lot of teamwork. I have the idea, I lead the whole thing, but somebody else does CFD, somebody and a whole team of experimentalists. It takes a big chunk, and only in Boeing and things you can do that, afford to do that even. So here is the same TKE with the regular chevrons. So now we are comparing different chevrons, regular uniform chevrons without and this. The thing is, this particular thing, if you come really close, you'll see that it is indeed decreased. Okay, it is pink. I can see it, and this is red. So you see it decreases quite a bit. But this doesn't capture. So I want to look at cross sections. So we did that, and NASA actually ran that and is through a CFD code. But so let's go directly to the cross sections here. It's the same thing, and this is CFD. This is not data really, but you will see that this is the conventional. This is conventional. I show it with a cartoon out here. No chevrons. Then this is what I call Gen 1. I call it GE chevrons because GE did this uniform thing, right? And I'm just showing it like uniform. And this is my thing. RT, T-fan. I'm just showing it as a cartoon, right? So that we can follow it. And these are the pictures. What do you see here? The baseline chevron, this is a cuts. Okay, I've taken a different, these are the different cuts at the same XOD. And we have done it for the whole series. I'm just showing you samplings. This is baseline. Out of all the things, this was with chevrons, with the Gen 1 uniform chevron. Look at this guy. It's reduced. And it follows through the whole cross section. These are the samples. I just can't. And my papers, we have all these things, and my papers are written out there. So not GE, NASA has a code to even actually predict the noise from it. Not a great thing, but at least these are CFD things, and I could see, yes, okay, this is what we are thinking in terms of fluid dynamics. You have to use both, right? So here is a kind of thing, and then we had data. So let me switch now to concept 2. The concept 1 was azimuthally varying chevrons, and concept 2 is long cowl nozzles, as I said. This is the lobe mixer. This is now another, it's not chevrons. What happens here is this is just a convoluted metal lobes, as you can see, right? So this is that same, the side view, it looks like a triangle. The fan flow is coming down, core flow is going up. Core flow is going up. This is a aft looking forward view, fan. So what do you see? Use right hand rule. Again, streamwise vortices are formed. That's the whole idea of the game. Streamwise vorticity, and they are very strong because now you are physically juxtaposing two flows with radial components in the opposite direction. Chevron was a gentler guy, he just does it like a wingtip, not like the jumbo jet wingtips, but we have just small immersions, and they're like few degrees, 3 to 6 degrees, etc. So this is a very aggressive mixer, and this is what it was in the, when they came into being essentially, and whereas so I said, okay, if it's aggressive mixer with that success in the normal chevron, why don't I replace this lobe mixer with chevrons? And I called it internal chevrons. This is the first time, okay, nobody had internal chevrons. Nobody had it in the industry, NASA, nobody. So this was a new idea. I said, why don't I replace this with internal chevrons? And I wrote a series of papers, and as I told you earlier, these are gentler mixers. Remember what I said, if it is aggressive mixing, and if it's of the same length scale, then it will create high frequency noise. Remember internal jet noise? Whereas I'm hoping that this would make lower internal jet noise. And what you see outside is a combination of both internal jet noise and external. I mean, there may be something that you give up because this if it doesn't mix that well in this distance, this may not be as uniform. Maybe its thrust efficiency goes down, and which is what happens. But I'll show you a picture where everything taken into account. Some of these guys, 1 hour lobe mixers. I wish it would go in some plane someday, So when I presented these the data, this is just the idea. I wouldn't go into all of this, but the thing was internal jet noise is high in lobe mixers. I'm expecting it to be lower for the reasons I mentioned, and internal here is the high frequency part also. Hopefully is lower, and perhaps the thrust coefficient may be lower than these guys because they may not form the uniform flow by the end because simply they're not mixing it. So there's always a give and take. You give up, and then there's the propulsion engineers who are the main guys who decide yes or no, and it depends on the thrust. But the noise guys can say you can't land even, or you can't even take off if you don't reduce your noise by X amount of dBs. So it's always a struggle. Okay, I have gone through these cycles many times, but so that's the idea. The third concept that I introduced, these are all my concepts. There is no other previous thing in the literature at all. Okay, was clocking. Again, and I presented papers, but it's always in conferences. So here, what I mean by clocking, you can immediately imagine if there is a pair of chevrons or low mixer chevron, etc. Can you think of? I can clock differently. right? I mean, I can keep like this, I can have valleys and tips, etc. What happens because of that? Simple fluid mechanics. That's the beauty of all these things. It's not CFD. I'm not even using CFD. I just draw pictures and then tell the CFD guy to check it out. You know, the validation of a hypothesis. But I want to do experiments. Let the CFD guys do whatever they want. But so here what happens, as I said, you have two sets of chevrons. I have 1-to-1 chevron here. Okay, so same number of chevrons and smaller and bigger. So here in the valley, this is going out, the inside flow, right? As I mentioned. If the tip sees it in the fan, what happens? These are small radial jetlets, they'll hit each other. What happens if two radial jetlets hit with a small length scale? They'll create high frequency noise. You don't want it. So this I call is not the good you know, simple things like design. Actually, I showed it in data. So what I'm saying is just clock it properly. What does proper mean? If this flow is going out, let also the valley and valley combine so that this goes out and it don't hit each other, the radial components of the jet. Same thing here and down. So they do form like nice cells. And let's see what happens. Simple idea, right? And somebody let me check it in a lab is a different story. So, but the ideas are simple. They are born from simple. So that's just about clocking. And I've used all that in all the Boeing planes. So let me say, it's not just academic papers I publish or anything. You go, you test it, and I test it. I've been in the labs like days and nights, just like academia. It's like going back to school. I've worked just like graduate students, right? You guys are there. So I did that, and our walls used to be full of data. And then others used to come and say, hey, that looks good, let's see. And that's the satisfaction feeling if the idea works, right, essentially. So valley to valley, and then you can apply the same thing. Now I said, if it is an internal chevrons, which I myself invented, we can have external chevrons and check clocking, and then you can have lobe mixers, and then you can do the clocking with lobe mixers also if you have chevrons, which are called external chevrons now. And I did all the experiments actually. Here, you can see the same principle, this lobe crest, now it's a crest, and the valley if it meets. Then you can create cells and the jets won't meet. However, one thing I have to say is with this thing, with the long mixers is, these vortices also decay. So if this is too long, all this business won't work as well, the clocking business. If it were coplanar or close, it will work, and we check that too. So just jumping the gun here, the vortices decay otherwise. So all this business about two radial jets hitting each other doesn't, in reality, remember, this is going with a high forward speed, up and down, so it goes like a spiral. These guys are spirals, okay? In reality, it's like, if you look at it from the front, they're going like this. I'm showing all the cross sections and all and simplifying things, but it's in reality, it is, spirals going out around. So in summary, the concepts that I introduced, I have some more ways to go. I hope I can do it. Azimuthally varying chevrons, you saw that. And we checked many. I'm not going to do that business here. Not just top enhanced mixing, I checked bottom enhanced mixing, I even check K-shaped mixing, I check combinations, whatever. And imagine each nozzle costs $35,000. Okay. So it's very expensive, this whole business. I was just fortunate that Boeing had deep pockets and I could test all of it. There's a beauty to this, and I'll come to that in my very last chart. If somebody trusts you, especially in industry, if your manager, and he had full trust in me, he said, blank check literally, and I said, just go and do it, get out with something that works for Boeing, right? So it's a product that works, and that's the pleasure you get. I mean, you try out things, and not that I know that this thing will work for sure. If you try out and something works, and then it goes into a product, and you see it. Now I can tell my kids, hey, I designed those things, literally I've designed those things. So it's a lot of fun. The work is fun then it no longer is work, and that's how I enjoyed Boeing, frankly. So now, scale model test data validation. I'll show you some data, and maybe I'll have to speed up a little bit. We have an anechoic chamber, wind tunnel free jet for the forward speed. We have a circular arc array. This is the nozzle, this is the wind tunnel. We also have something called an acoustic phased array, which not too many people have, maybe some academic, but this was one of the largest arrays in the industry or the world. What it does is, these guys just measure at that spot. What am I hearing? They don't know, normal microphones don't know where the noise is coming from. Is it coming from here, or where, right? Phased array, what it does is, it looks at the difference in time between very teeny weeny distances of microphones, and you can pinpoint where the source is. That's a very diagnostic tool for aeroacousticians. They'll know it's coming from here or here or here, and then there are some errors, of course, but you'll know where the major sources are, and then you will know, okay, what to do about it. So that's the beauty of acoustics. There are experts. There were experts in my, my team who were, they designed acoustic phase arrays. They wrote chapters in books, and they're really great guys, So we had the ability to move it, traverse it at different angles. Remember, angle is very important, because at this angle the source may look bigger from here, and at this angle it may look bigger somewhere else. So it's a fairly complicated picture of 3D picture. At least you are circular. When it's rectangular, things change. So you even have to look at azimuthally how the noise is varying. So it becomes complicated. This is the phased array. These are the kind of microphones that we have on a plate. These are logarithmic spirals. But these are the kind of X-ray plots, let's say, that we can produce. And I'll show you some if I get time. So let's go quickly on these pictures. This is the near, just a close up on the picture. This is the wind tunnel, 7 by 10 feet. And this is the pylons. We always have pylons. And the pylon is kept like this, not like this, because the microphones on horizontal circle. So long as they're underneath the pylon, it's okay. And we can rotate the pylon to get the side angles and stuff like that. So this is a close-up. You can see all these internal chevrons. You can see this azimuthally varying is fortunately captured somewhat. All right. And so let's see the far field SPL. Now here comes the beauty. And here comes my eureka moment in another slide. Okay. This, and pay close attention, because you will need close attention, and it gets slowly more complicated the way I present data, but I'm trying to simplify. Here is the baseline. We always compare it with no chevron, baseline data, right? Then you compare it with my T-fan, that was my first thing. Then I'll compare it with different combinations. But first I want to check this T-fan, and I'm going to give it at the 120 degrees from this axis. Because remember, different angles, it changes. But the real important one, remember, directivity as a jet noise. So first is just representative. What is it showing? I'm showing here, first of all, the 1/3 octave band frequency. I'm not going to go too much into it, but it's 10 log frequency. Because scales are so big, we have to do a logarithmic thing. And this is, we call it frequency bands. And here is the SPL that you already know, I talked about. What happens is, in any practical anechoic chamber, since we run it at some Mach tunnel number 0.3, which is not that low, tunnel itself makes big, right? It's a big, so it makes noise. And you see low frequency, yes, it starts competing with jet noise, so we throw that data out, because this is all contaminated with the wind tunnel, so we throw data out here. Same, there are other things going on with the lip, and they reflect and all, and we throw that data out. But this is the data, is very useful data for full scale, and we are doing it at model scale. What I'm showing is model scale. But remember, now the beauty of the T-fan, this is the baseline. It decreased noise considerably at the peak. It did not increase anything in the high frequency. Correct. I mean, this is the kind of thing, and it is just one T-fan. I have not done clocking, I have not done anything yet. This is just one T-fan, but so something worked at least at that angle, and then we'll show some other angles. So this was the same thing. This is the same thing, BB, TT, TB. Then I have the whole angles. So focus now, because a whole bunch of things are going to come up. This is at the very aft angle, so it's like 150 degrees. Even then, it gives me good amount. Remember, the scale is different. It's 100 dBs. Here it was 95, the peak. So scales are slightly different in this whole aft, what we call aft quadrant, behind the 90. So this is also aft quadrant. So here the scale is different because the noise is less. But here the noise is more, but still baseline is much higher. My T-fan still is doing great job, and it's not, the high frequency didn't increase. So that is very satisfying, when the meaning earlier I showed you the other guys, that data showed high frequency increase and it kills the whole effect, right? It somehow didn't increase, and that idea, that a concept that I told you, have big, have small, seems to work, luck or not, you apply basic thing, first principles, it seems to work. So then you go in the front, which is not as important for more, but it still shows, this is baseline, this is in the front quadrant, okay, and it's not as important for jet noise. And still it doesn't increase the high frequency, it reduces low frequency. So how would you capture all of this in one picture? Contour plots. So the idea is to just look at the deltas. Absolute value is important, but delta, if you see the difference, if it is negative, you have done the part. I mean, some places, if it shows increase here, but absolute value is so much lower. Remember what I said, If this is 10 dB lower, the small changes here doesn't do anything to the whole integrated OS. So I show an OSPL. So this is the baseline. It is reduced to all angles. This is angle now. So it is each point I've integrated across all frequencies, and still it shows pretty good. But OSPL is not the real thing. In academics, they show always OSPL. But even if OSPL is great, your PNL and EPN is what matters, perceived noise. In this case, it will just do a great job because it is doing, across all frequencies and all. But so this is like a key example. Now, the whole data can be shown in a contour plot. What am I plotting here? This is the microphone angle axis. And this is the same 10 log guy, band number we call it. And all those deltas now are put here. So what's the scale from -3 to +3? It's just the delta dB, all right? So here you get the blue. Anything blue is great because minus. I'm subtracting T-fan minus this thing, right? SPL difference. And all this is great. This is very small increase, 0.5, etc. Remember, absolute value is going down here, and these are the other things that I throw out at there. So this is good. So it will give essentially just T-fan gives, and I want to show you with the other combinations. So here it is. I'm going to show for Gen 1 or GE chevrons. This is the baseline. So the difference between these two. If it is negative, great. If it is positive, not so good. And the difference between this RT guy and baseline, because that's what we want to compare, right? Now that's the beauty. Now this plot is the eureka moment that will come. First of all, the uniform chevrons. I call GE chevron, Gen 1. Okay, blue, it does a great job. I mean, it does a good job. Let's say it doesn't do a great job. But the bad part is the pink guy is increasing the frequency, high frequency, because it was not designed really with all these details that I'm telling in mind. So, and I designed it, so it's not like it's GE design, I designed it. But I gave my best shot with uniform chevrons with that restriction, and it increases jet noise simply. Now, here comes the moment, guys. Boom! This T-fan, I want this blue to spread everywhere, right? This was our eureka moment. I mean, this blue, it doesn't, it's way beyond -3. This is -6 dBs. If I draw contours, I just want to keep the same scale, color scale. And it covers a whole range of angles, and it is the frequency of interest. This is the peak, where the peak is. This was our eureka moment, okay? Where people, when they came in our labs and looked at the board, they said, this guy is a winner, and we have to do something about it. And NASA guys came and they're like, wow, we got it, we got something, it's a mini breakthrough of sorts, really, when we see a plot like this. That's why I give it a star. And then we went ahead and did lots of experiments on that. And as I said, I've studied several other AVCs, azimuthally varying chevrons. This was always turned out to be the best for whatever reasons. I tested bottom menace, I studied K-shape and combinations with this guy. Here, by the way, when I say R, the core guy is uniform. The top end is only the fan guy is the outside. And it turns out in terms of logistics or politics, the airframers make the outside fan nacelle. That means Boeing makes it, not GE. And GE makes the inside. There's always a tussle, okay? And since we have the patent and designs, Boeing said, we are going to make it. You can do this. And if it sells more engines for the engine company, they said, sure, you give your stuff. And that's the way it goes, So, and these are made of composites, the fan. This is metal. This is metal. It's a high temperature thing, right? But they make, the engine company, because I've worked in it, I know it's such a high precision thing. Even the plane is okay. It's what we call tube and wings. We can do things, aerodynamics is well known now, other than supersonics or hypersonics. That's a different story. You're about subsonic commercial, right? But engine is a very tough area. And especially, these turbines and all, because I worked initially in turbines and compressors, the front end, then I worked at the back end. The tip clearance for a turbine is fractions of millimeter. It is super. I mean, the engineering marvel is super. And when I went in the end to Parker, I was trying to control that distance I told you at high temperatures. So I covered that area also, and I can appreciate how difficult this thing is. We always appreciate, computers, of course, fantastic things, right? And they deal with nanometers. But our mechanical stuff, which we do at a big scale, and we still have to control it at fractions of millimeter, is something you have to appreciate. You have to go there and see it, to really appreciate that. So I've gone through that whole thing now in last, 50 years or something, and I can appreciate that as an engineer, as to that these guys are great. So acoustic phased array data, I'm at this, right? Okay, I'll quickly go. I'm not going to spend too much time. Oh, already over? Jeez, I'm going to go fast, okay? But I'll just touch on some basics. So this is baseline, this is noisy with the pink color at some frequency. The T-fan alone did a great job. You can see, right? This is the GE chevron of Gen 1. This is my RT, the great guy. It's just, at that frequency, at least it seems to have made very little noise. Essentially, it shows up on the SPL, but this is at the source. So I'll just quickly go. These are higher frequencies, and we know why higher frequencies. Remember at the chevrons, it comes closer and closer to the nozzle. So this is the source now. We are looking at a source, okay, not like the previous case. So I'll go fast. I'm not going to show anything with the install, but these are kind of install planes that we have, and these are different photographs. This is through the wind tunnel. I'm inside the wind tunnel and showing this. It's fun, you know. It's a big, huge 7 by 10 feet wind tunnels, and I was inside it. There are all kinds of features. Anyway, so then we have, you know, flap. I did a whole jet flap interaction. I have a whole series of papers on that in 2013 or earlier. So the jet interacts with the flaps too, and the jet flap interaction is yet another source, and you have to account for that. And I did a whole separate test for that. But these are some of the pictures. I don't think I'll go with the data. It shows the interaction from the jet and the noise. And again, RT, the interaction even is low. Good for us, right? Fortunate, whatever it is, it works. So other frequencies. So after all said and done, we tested it on a full scale 777-300 ER. I fly that. I just came here in one of these planes. Well, of course, not with this engine. In a development stage, what happens is you replace only one engine because the other engine better work, and it doesn't do anything. So we replace. Oh, please! I know Boeing when I say, you know, what happened, but I don't know about it. I've left Boeing many years ago, so don't ask me anything about all the things that have happened. Unfortunately, I have to say, no, Boeing is a great company. And some things have happened, and it goes, and please don't ask me anything. I have no idea, I have no clue. But so this was the first thing that we tested in a real. So this is a fantastic photograph in a takeoff mode. They tested other things also, but this was the only thing that really went into a product finally. So this was a G90 engine, and they just checked with one engine, etc. And then it went into actual product. The 747-8 was my first, you know, actually I designed these things, okay. And you can see that. Then it went into, you know, 737 MAX. We developed this. Blue is the developed 747-8 737 MAX. The 787, the Dreamliner, is not my design. It's a uniform chevrons for different purposes. It's only for cruise noise, jet noise for takeoff. Somehow they said wasn't an issue. I never looked at it, so I don't know. But this thing would work even better. It would reduce their jet noise, you know. So I won't go too much because I'm out of time really. But I worked with chevrons that I was telling you. I checked out clocking, I did all these things, and remember they don't exist anywhere in the literature, this internal chevron business. I was lucky to just have that idea and test it, and it worked. So I'm not going to go through this. What it shows is lobe mixers versus internal chevrons. You know, there is a blue is more noise with the lobe mixers. I remember I was saying it creates high frequency noise. Here you go with internal chevrons, same number I kept because, you know, the number of lobes and it is pink. It did decrease. It worked, okay, intentional. Now the fact is, maybe, you know, I'm just comparing this. If similar lobes found for 18 lobes, so it's not a fluke. It's not just 14. It worked also for 18 chevrons. So clocking I checked. Now don't worry about this complicated figure. What it tells is clocked versus unclocked. I'm giving a difference, and exactly at high frequency it reduced. So that thing worked. You know, some things that I told you about the radial jets hitting and the high frequency increase. The darn thing worked. And it shows, and I captured it in other things also. So now is one of the charts I could show is noise versus thrust. And what happens is the thrust, you know, this is like we run at the same operating condition. It moves a little bit here, a little bit there. But at least when you quote it in the same thrust line. So this is baseline. So obviously it's much noisier. And these are lobe mixers and mixed with chevrons and things. And imagine this red guy was my internal chevron and external chevron. This is the red, is the lowest. It is giving at the same thrust this much noise, and this is considered to be large, okay guys, 2.6 in terms of the EPNL. EPNL is a very integrated metric, and I mean, so this is like up there available. And one thing, just small, this thing is, when I presented this to, and Pratt and Whitney guys were there, they had worked a lot. They are great lobe mixer designers. They said, you are staying it, and we also got some, we never published it. Boeing let me publish this, okay. So they said, you are correct, we have this, but it's not in any product, unfortunately, but it works, the idea has worked. So anyway, aerodynamic performance was slightly, off. So future, this is just one real, okay, because you told me about the SMA. If any material scientist is, that's my third department I was supposed to satisfy, aero, mech, and it's very interesting. So I'll just do this and then I'll summarize. I won't show you the other because this is interesting. Remember what I said, at takeoff, we want it slightly immersed because that generates strong vorticity. But it also may give some loss if you don't do it properly. So at cruise, we really want it in a different angle. We don't need that noise reduction. So if I bring it up, there won't be any thrust loss. So how do you do up and down? Now you're thinking of movable things. Temperature is different. Up there in 35,000 feet is cool. So this is my friends doing the shape memory alloy is one of the things, okay. I designed the chevron and told them what immersion, but they were the guys who tested the shape memory alloy part, and I'll tell you, it's a very interesting thing. If you don't know, at takeoff with hot, it is an austenitic phase. It is not like bimetal strips or anything. It's not like that. It's literally difference in the phase of a material. It's called austenitic phase at hot conditions and martensitic phase. The material changes properties and it changes the stiffness. So you can make it memorize one shape and memorize two. Okay, so we did that. My colleagues actually had, so I have a picture. So we did different things here. Remember, this was the T fan, it's immersion I'm showing. Near the pylon high things, it's a cartoon, right? But now with this kind of thing, we also could control which chevron I want to dip more, which not. So I did this to imitate that. We did this to see for shock cell, meaning cabin noise. If I did some other 3 o'clock, I call it, and I have charts and papers on that, how it shows how interior noise decreased because this playing around with this immersions all around the periphery. So I'm not going to show any this thing. I have papers, etc. So I just want to show the cross section of this SMA chevron, shape memory alloy. It is made of 60 nitinol, which is nickel titanium alloy. It's called nitinol. 60% nickel and 40% titanium, and it is these are strips which are made of that material, and they change shape and they bend the composite fiber chevron, the substrate we call it, and they can bend it and they train it. They train it so that it takes shape 1 and shape 2. And in this case, because it is a developmental thing, they also had heaters, actual heaters. It's supposed to be autonomous because we wanted to control at different angles, etc. Right? While during flight, imagine it's during flight, we can change the angles because of that phase transition. And we had heaters in this particular flight. So there are 2 operating modes. One was autonomous, just the way I mentioned it. It will go by on its own. There is nothing controlling it. But the other one was controlled, and we had heaters and of course strain gauges, etc. measuring it. So all these details, my colleagues did it. So I write it in. They have a patent and they have papers. It's not my stuff. But I did give them, what shapes to cut it, what immersions to dip it, and all this was my idea that we should do this, and we checked it out, it worked. So with that, I'm not going to go into this, we can discuss on the side. This was the concept I was trying to tell you. So you can always think of mechanically drawing in and out, simple idea, right? And I've applied for a patent with a couple of my colleagues. This idea was nice, but I don't have the time, I think, to go through it. This is in the boom supersonic when we are doing, and I can say it because I got a patent just last year, just few months ago actually. We got a patent and it was the fastest patent we got, It's very hard, by the way, if you guys go at some point and apply for patent. It took me 6 years for my first patent. And software guys get it in 3 years. Wholly different story, okay? We mechanical guys, when we go, we fight it out, our lawyers will be there and their lawyers will be there, or the patent examiner. It's a hard thing. I have 20 patents, so I've gone through this whole cycle, okay? And different things. But so here, I was just showing, we have a lobe mixer. In the supersonic plane, things are rotating, so it's circular geometry. But there are ways, people say, rectangular nozzle shape in supersonic flows has other advantages. It can be fit properly, etc. And also, if it is a rectangular aspect ratio, it can reduce noise. It flips angles and stuff like that. So there is a transition of shape, right? From circular to rectangular. What happens is there is a, if you look at the fluid dynamics of it, and there is here I am showing something called an ejector, is a third flow, you need it to slow down, slow down jet so that the noise reduces. So they have an ejector, and it came about because of thrust increase. They really want to increase thrust with this third flow, they mix ambient. Before even this guy, they just want to mix it with all this mixed flow. But what happens is this this complicated transition geometry from round to rectangle squishes all the fluid mechanics. It's screwed up, and I didn't know what to do if I want to place a chevron here in between. That's what I was trying to tell you in the lunch. If I want to place a chevron to even mix it better from the lobe mixer, I don't know what to do here or how to even select a number of chevrons, right, or where to place it. It's just the whole fluid dynamics. If you look at CFD cross sections near this area, it's all a gobbledygook. And we have our patent has the published, colored, all in colored. But when you come slightly downstream of this at the exit plane, things start relaxing and they start getting quasi-periodicity, spatial, span-wise width. Meaning they look like, okay. So my idea was, and you can appreciate what I'm trying to say here. I said something is happening downstream. I'm going to adjust the number, immersion, etc. I'll tune it so that according to the downstream guys, when I don't have that. Do you get that idea, what I'm trying to say? You run a CFD, now here I need CFD or an experimental data, but CFD was easier. I don't have this guy, I have this guy. I see a quasi-periodicity, I don't see any periodicity or anything width-wise. And my idea is, I'm going to fine-tune this such that I'll literally like a resonance, spatial. I'll amplify those things so that those vortices etc. become stronger and my mixing is better. And it showed in CFD data because I never could do an experiment in this. But ideas are what matters for patent at least. And unfortunately, that they are using some other engine etc. I left it some years ago. But this was an idea which was I thought was very nice. You fine tune it something before it happens. And that I've never seen that used in jet noise and stuff, okay? Because you don't know what to do at that plane, but you know what happens there through CFD. Then you say, I'm going to fine tune it, the numbers, the angles and stuff like that so that it works. So that was one of the things, and I think I'll quit at this point. Summary, I'll quickly go. Jet noise reduction very challenging, increase in high frequency and thrust, new concepts, azimuthally, AVCs, clocking, internal, SMA I showed you, and it was a win-win-win. Now, why is the third win? This is of course noise, thrust was hardly any loss. The third win which I never showed you is the shock cell noise. At cruise conditions, there are shocks in the jet and it creates something called shock cell noise. And it turns out the shock cell noise was reduced in all of these cases that I showed, and I have papers on that. So it's fun, I mean, you go and put mics inside the fuselage and they're dummy, heads, mics, everything. And my colleagues who do that, they're more into it, and I was just sitting as an observer saying, is it working or is it not? And then I analyze the data, right? And those are the papers. But it worked. So that's the third win also. And doesn't happen all the time. You don't get a free lunch. It's like, okay, I got everything done properly at least. So, okay, last point and then I quit, guys. I see Aniruddha is saying clock is ticking. I'm okay, right, guys? Because it's now what, 6:48. It's way beyond. I thought so small innovations can go a long way. These are all really small innovations. I really have doodled it, then you refine it, talk to your people, get some funding from NASA or Boeing if Boeing had money or GE or whoever. It goes a long way, when the right flow physics, that's what I want to impress, You have to use the right flows. It's not that you do some very fancy thing up to the 4th decimal place. No, I don't believe that. The germ of the idea is in your head. You have to draw it, you have to bring it and test it. Without testing, nothing. CFD are still, or computation is still not at the stage. I mean, I talked to a great guy called Philip Spallart. You may know him through Spallart-Almaras equations, right? And we were in a competition and when I joined Boeing, and my manager said, okay, you do competition, I'm going to do experiments. I'll get faster results. We got it much faster. They're still struggling, those who do computational with plus minus 3 dBs. My repeatability is plus minus 0.3 dBs in the lab. Because if it is within 3 dBs, I don't even know whether my concept has worked or not by doing computational study. So I know I'm not I do theory and then I jump to experiments where everybody can compare. lots of guys do computations. There's lots of PhD theses are CFD or CAA, and great, I think you discover science there, I understand, if you do apply the right thing. But so far as applications are concerned, if you use the right, along with the right facilities, team and funds, you have to have funds, team also. And so I give acknowledgements to funding from Boeing and Rolls-Royce and all the fellow engineers. There's a huge team. It doesn't happen just one person. It is a team effort, and I do want to impress upon that. So I think I quit.
I'll ask one question.
Sure, go ahead.
What was the effect on cabin noise, like dB level on cabin noise?
I'll show you in the papers.
Okay.
Considerable. The shock cell noise, it is spatial also, right? In that case, and it's not near field, midfield, and it also goes through the cabin insulation and all. But that's the same. You change the concept outside, so that part is same. So, and I'll show you picture. I don't have it right now. It changes considerably on the side of the engine that was modified. Right. On the other side, it remains similar. That's our controlled in case, right? And then, so it is quite a bit of dBs. The thing is, the cabin noise is not controlled by any certification rules. It's so-called OSHA. Federal Aviation says we don't care about inside passengers. they can have all the noise in the, but it's still reduced. This concept turns out, fortunately, it reduced, and we proved it through data, and I have few papers on that, and I can show you some things when we meet again. You saw we are even going lower with these kinds of things. Actually, no, because the constraints are there because we are making progress. Okay, because we make progress, okay, you guys can reduce it. Federal guys will say, place it harder, place these guys harder and harder. It is going down. That first chart that I showed, right? And I have another chart which captures that it is indeed going down. So and they are reasonable, the FAA folks are reasonable. They are themselves engineers and stuff, aeroacoustics. So no, I believe it will keep on going.
What you're saying is that because there is improvement in noise reduction, there will be more regulation, it will be tighter.
Yes, and also because some communities really complain, they are very vocal. I'm telling you, where I live, it is strictest noise control in the whole of US, Irvine, Santa Ana Airport. That's where I live in that neighborhood. I'm further away, fortunately, my house. But people are very vocal in US. In Europe, even more so, guys, they are very, if they'll go and complain. And complaints mean, then you can't, in the planes can't fly before 6 a.m. in our airport, which is the nearest to me. Yeah, they are curfews. And 11 p.m. So 11 p.m., 6 a.m., you can't land, you can't take off. So if I fly back to that airport, I have to fly within that time, adjust, etc. But hey, it's good for the community. So it's a pretty community, driven phenomena, really. How much noise you want to reduce, and it will keep on decreasing, And this is jet noise. I didn't talk about fan noise. There are lots of things that have happened in fan noise area also. So that's, yeah, sure.
To the upper side.
I was talking to somebody in lunchtime, yeah.
So and we saw that.
That's not jet engine though, okay. That's at cruise, it is the shock wave and the bow shock wave that comes with the plane. You know bow shock wave from the nose and the wings, but it's a shock wave, so it's not from the engines. And you're right, actually Boom showed it first, okay, and Lockheed is there with their big things, but it's the same phenomena, and you have papers you can read where it reflects because of the temperature change, the shock wave, so it doesn't even reach the ground. So now you can fly supersonic planes on the ground. They are restricted to fly only on the sea. Up till now, Concorde only could fly on the sea. It couldn't fly on the ground from east coast to west coast, let's say USA, because I'm familiar with that one.
It was basically because of that shock wave, not because of the
noise. Yeah, that is a difference. It's not engine thing. It is a shock wave coming from the nose and the wings of the plane. And if you don't do it, it's pretty strong enough that it goes down. But if you go very, very high, instead of about 35,000, if you go to 65,000 feet, that's where they're supposed to fly. They also need to know the temperature profile. That's the key thing, Right. It refracts it back literally. It gets weaker and weaker, and then it reflects back. So it goes up. So who cares, right? If it goes up, I asked the Boom Supersonic CEO because I was working with them. But later on, I asked him recently that hey, if a plane is flying behind you, he'll feel that noise. What do you do? Who cares? It's a community noise is the key thing, and Federal Aviation is dealing with people. They're not. They say, I asked him a question, they're not thought about it. I said, okay, it reflects. I have another plane, it may be 10 miles, 15 miles away. He will feel the shock, and the noise. He said, okay, weird. We know always ask weird questions. But so that's the way it is, But good question. But it's a wholly different thing. That is a wholly different shock.
Why did we use that Chevron concept in
Oh, these patents.
I thought it was because of engine.
No, that one is really, if you learn aerodynamics, it's the bow shock waves which come from wings and nose and things like that. It's really that is the large effect, not because the engine is running at a different operating nozzle speeds and all, and the noise is there, but they don't create that much, shock cell noise, etc. So, sure. Yes.
So talking about gateways in my house.
I'm talking about what?
So gateways.
Oh, okay, sure. I can answer the weird questions too.
So all the chevrons that we see, that it's all in the inverted kind of a shape, right?
Right.
So the function is to have more turbulence.
Right. No, not more turbulence, more streamwise vorticity. Right.
So why not get any other shape in that?
I have another slide backup chart where I tested all kinds of shapes. The thing is, first of all, you don't know whether you want, and initially I thought about it, being like this. You don't know whether that's the better one than this. So we did test, G tested those things like this. They thought spoon shaped thing is a better thing. It didn't work out. So those kinds of shapes were checked out in the beginning. And it turned out, typically it depends on how many number of chevrons and circumference and what kind of optimal angles you want. Because as you were asking, man, that's not difficult. Because if you can have longer and longer with the same circumference, it will become like this. And those vorticities don't help really. If you make it longer but keep the root same and make it longer, right, it becomes like this almost. And by the way, Rolls-Royce did this, and I was like mad when they started doing trapezoidal chevrons. Meaning, I told them, you are losing real estate by having this thing. It's not creating streamwise vorticity anymore. They had that when I joined Rolls-Royce and told them, please don't do it. So they didn't do it in the end. But sometimes they freeze designs, and that happened with the 787, the Dreamliner. I wasn't there in Boeing, and some other guys did it, and now it's fixed. Because when they freeze a design, that's what it is. They freeze a design, and I came a little bit later, 2-3 years later. I joined. So you see, all the Dreamliners have just normal chevrons, and stuff like that. But later on, the 747-8 and Maxis, you will see. By the way, you will ask me, hey, they look uniform. If you fly someday, then why? How come it's azimuthally right-wing? So what's the answer? If it's the same length, what else can you do? Of course, immersion you can change, and I showed you. So they look similar, but it's a subtle variation in immersion, and we tested that. It works well. It's just the tailoring of actual vorticity, what I call it. And if you do it the right way, you get a noise reduction, and there is no thrust loss. So our answers for thrust loss, I didn't show much. It's plus minus 0.04%. That's like within error of margin, And one of my colleagues was the lead author in that, because he did flight test with the propulsion. I was the second author, but I didn't show anything. I have a whole bunch of papers on these guys. So it has been fun. It has been a lot of fun. So if you are aeronautics, aeroacoustics engineers, a lot of interesting things are still there, So look for, I don't know how many of these are aeroacoustic students, but.
So I'm teaching aeroacoustics next semester, so you're welcome.
Oh, yeah.
For me. But
okay.
So it's my pleasure to hand over this memento. Yeah.
Thank you so much.
Thank you very much.
Thank you so much.